This is the 19th lecture of the course, MTH 204A for section B. Recall that in this course we have already started classifying groups of smaller orders. The abelian groups, all finite abelian groups have already been classified in the next lecture, and some non-abelian groups we have also classified, namely groups of order 6, groups of order pq for any prime p, groups of order p times q for any two distinct primes p and q. So this we have already classified. So we will continue our classification in this lecture. So far all the classifications that we have done, except of course this very general complete classification of the abelian groups. So that's a completely different thing, where it gives us a complete list of abelian groups for any natural number n. But so apart from that, all the classifications that we have done, let's say for order 6 or order p cube, those things were typically, we were looking for the non-abelian group structures more, because as I said, abelians are already taken care of by the structure theorem. So in those setup, it is already, we see that the first step of the strategy that we have adopted is to find two proper subgroups H and K such that the given group becomes the semidirect product of H and K. And while talking about the semidirect product, automatically this automorphism group of H will come up. So it's inevitable that in the strategy that we have adopted for classifications of groups of smaller order, automorphism groups will appear. So we should try, and in fact we have to try to simplify them as much as we can. So in order to simplify the automorphism groups and subsequently the semidirect products, we need the following. So again, as I said, I would like to tell you that this, what I am going to talk about is not the case always, but however in some cases, particularly in this course, because we are going to deal with the groups of smaller order. So this indeed what I am going to talk about, this indeed helps us a lot to simplify things. Okay, so I should rather define that. So what we are going to define is something called the characteristic subgroups, or in other words, fully invariant subgroups or strongly normal subgroups. So given a group G, a subgroup is said to be characteristic as a characteristic subgroup of G if for any automorphism of, so if H is invariant under every automorphism of G, if for every sigma in G, sigma H is H. Okay. If a subgroup is invariant under all automorphisms of G, then we call it a characteristic subgroup. What are the examples? First example is, if G is cyclic, then any subgroup of G is characteristic. Okay. So as I said, some authors call it fully invariant subgroups because it's invariant under the full automorphism group, or some people call it strongly normal. We'll shortly explain why this is called shortly normal. In fact, it's easy to see that, like that this implies, so okay, I will put it as a note a little later. Okay, so why this is true? Because for any given order, there is a unique subgroup of that order if the give G is cyclic. So in fact, this is rather something follows, this is a consequence of a more general thing. So it says that if H is the unique subgroup of G, having a unique subgroup of G with a given order, so what I mean by this is, suppose this has order m and H is the unique subgroup of order m of G, then H is characteristic. Okay, so let me introduce a notation here. If H is characteristic to a characteristic subgroup of G, then we will simply write it as follows. Okay. Okay. In particular, as a consequence of this general thing, if G is finite nilpotent, then any silo subgroup of G is characteristic. Any silo subgroup of G is characteristic, because earlier we have proved that any silo subgroup or a finite nilpotent group is normal and all other silo subgroups are conjugate to each other. Hence, corresponding to any prime divisor of order of G, the silo subgroup P is unique. Okay, the silo subgroup is unique. So, in sense, from this it follows that this is characteristic. Then next, so this nilpotent group, this reminds me the following, which holds for any general group G. For any general group G, the sequences Z and G. The sequences Z and G is characteristic subgroup of G for all n. Okay. This is an example. In fact, the verification is left to you as an exercise. It's a routine verification. So, at least for center, it is the verification when n equal to 1, that is the group is center, then it is easy to see because an automorphism preserves center. I mean, it sends the central elements to central elements. And in fact, this is precisely the idea to show that higher terms in the upper central series, they are also invariant. Okay. Now, also for any group G, we do have this lower this another commutator series. So, this is characteristic subgroup of G for any n greater or equal to 1. So, in particular commutator subgroup, double commutator, all these commutators, all these are invariant, all these are characteristic subgroups. Okay. So these are some common examples. We are going to see more examples in the course of time. Now, let me put the reason for calling this strongly normal. So, for any given G in G, remember this Ig belongs to, Ig is basically conjugation by G, and if H is characteristic, then IGH, which is GH inverse is H, therefore that shows H is normal. So, okay, let me put write this directly. So, Ig of H is GH inverse. So, it shows that H is characteristic subgroup, then H has to be normal in G. However, the converse is not true. So, the exercise is find a counterexample. Exercise, find a counterexample. Counterexample. Okay. So, yeah, so the characteristic subgroups are normal, but the converse is not true. And one more thing which I would like to put as under this remark is earlier we have seen that if H is a normal subgroup of K and K is a normal subgroup of G, then H need not be a normal subgroup of G. However, the following is true. Suppose H is a characteristic subgroup of K and K is normal in G, then that forces H is normal in G. Okay. That's precisely because of if you consider the conjugation by a group element G, then GH G inverse is GK G inverse equal to K, since K is normal, and okay, so since this is a characteristic subgroup of G, from that we can immediately conclude that this is we can immediately conclude that this is H. Okay. Yes, so how does okay, I think I have swapped the order. Yes, sorry. So if K is a characteristic subgroup, all right, then H is normal in G, yes. So then this is this, and so the normal subgroup of a characteristic is 0. I think now this is fine. Anyway, but the thing is, the point was that just saying this H is normal in K and K is normal in G implies H is normal in G. That is not true. Okay, all right. So now I should come to the main point, that what's the main point of bringing these characteristic subgroups into the picture. This is the following, that the reason is that, as I said, that we want to classify semidirect products which will appear, and the semidirect product that already includes the automorphism, some automorphism groups. So now I am going to show that we are going to see that if a given group is decomposed, if it is decomposed into the direct product of two characteristic subgroups, then we can simplify this automorphism group. So what we are going to see is, basically you can record it as a theorem. HK are the characteristic subgroups of G, and G is isomorphic to H direct K. Recall that what this means. So as I have already said, that unless otherwise mentioned, this isomorphism is precisely this map. Unless otherwise said, by this isomorphism I always tacitly assume that this is the isomorphism we have under consideration here. Then we have the following: odd G is isomorphic to odd H odd K. And how to show that? In fact, the proof is very easy. If you belong sigma here, then since H and characteristics, so sigma H, so this is an automorphism, so sigma restricted to H is an automorphism of H, right? Is an automorphism of H. Similarly, we have sigma restricted to K, this is an automorphism of K. So therefore this we do have this map here, and then it is easy to see that since H is the D, and since this is the isomorphism we are having here, so this map also establishes an isomorphism between this and that. Okay, because the main point is that given two automorphisms of H and K, from that we can consider an automorphism of H in view of this isomorphism. So that shows that this map is onto, and oneness is also obvious. Okay. So this is what is going to play the main role subsequently whenever we have to whenever we need to simplify the automorphism groups, groups that are going to appear in our discussion. The next thing is how to simplify semidirect products in using this so how to simplify semidirect products when we are having characteristic subgroups. So we have the following, that all right, okay, I think still there I have made some mistake, no? Yes, it seems rather somewhat wrong. Okay, this and maybe this. Yeah. Yes, yes, yes. This is now perfect. Yeah. Characteristic subgroup and normal subgroup is normal. Okay, yeah, fine. All right. Okay. Because this GKG for any given k, GKG by conjugating elements by G, that gives us that gives an automorphism of k, and that automorphism is going to fix H, since H is characteristic. Yeah. So the first one that I wrote was correct. Anyway, now let's go ahead. So as I said, we will simplify the semidirect product. How to do that? So suppose simplification of semidirect product. Okay. So suppose we have given a group G and we have two characteristic subgroups H and K, and also suppose we do have this. Again, let me remind you, if unless otherwise stated. So this means the isomorphism which is in the consideration is sending H comma K to HK unless otherwise specified. So suppose this is the thing which we have, and let R be another group. When R is another group, together with, suppose we have a homomorphism from R to aught G. Recall that this is nothing but aught H, aught K. Okay, this is isomorphic to that. If these are the things given, then we want to consider the automorphism with this semidirect product. Okay, so which is nothing but, we can immediately see that this is the following is an isomorphism in view of this, that H direct product, K semidirect product R. So this the homomorphism here which is appearing here is actually quite natural, that I will explain in a moment, and hence this is omitted from the notation. So if these are the things, then if suppose H is the direct product of two characteristic subgroups, then for any other group and homomorphism from R to aught H, this happens. Well, I think I missed something. Yes, of course I have missed something. If this happens, that if R is centralized by, if R is being centralized by H. So let me first try to explain what this means. So in this semidirect product, what it says that every element of R centralizes H. So in this group what it means is if we take H to be in H and then R to be in R, then R H R inverse is going to be H. Okay. So this is suppose this is the situation. This is what it means, and this is my group which semidirect product that I would like to simplify. So the proof for this is the following. Let me again just repeat that suppose a group is isomorphic to the direct product of two characteristic subgroups, and then let R be another group with an homomorphism. If in this semidirect product this H is being centralized by R, by every element of R, then this semidirect product takes this form. So let me first show you why this is true. So I am just giving a sketch of this proof. This is a simple verification. So any element in G can be written as H times K uniquely for H and K because of this. So HK comma R, we should map that to H comma and here K comma R. Okay. So of course I should say that what is here. So this is nothing but from R to, we have this map, right, homomorphism from R to aught A, R to aught G. So corresponding to every x here, phi x is the automorphism of G. We restrict phi x, we restrict phi s, phi x to k. So precisely then that gives us an homomorphism from R to aught k. So again let me remind you, R to aught k is nothing but the restriction that is obtained by restricting all the homomorphisms, all the automorphisms corresponding to the elements of R, restricting all the automorphisms to k. Okay, that is the homomorphism we are considering here. Now once if we see this, it's a routine verification that this is an isomorphism. Therefore, so what's the essence of this proof? What's the essence of this simplification? So if this is the direct sum of two characteristic subgroups, and if one of them is being, if on one of them this R acts trivially, then the semidirect product is nothing but the direct product of this and the semidirect product of this R with this copy, with the other subgroup. Okay, we will see the application of this several times in our, of course, in today's lecture and in the subsequent lecture, maybe in the next lecture, of course, because in view of this, we can indeed simplify this semidirect product as a direct product of some of this subgroup H, which is being centralized by R, and this semidirect product. Okay, so here you see that this simplification happens when this so in this semidirect product, when this normal factor is the direct product of two characteristic subgroups of that. So the natural question is, do we have any counterpart? Do we have any counterpart for the non-normal factor? Yes, we do have. So let me also write that as well. The proof is also exactly done in the similar manner. The proof is also in a similar manner. So how we prove is the following. Okay, so as usual, that suppose H, K and L are groups. Okay, H, K and L are groups, and suppose we have K cross L to aught H. K cross L to aught H, suppose we have a homomorphism which enables us to construct the semidirect product. So H semidirect product K cross L. Okay. So analogous to that, we are going to simplify that as the direct product of some semidirect product with another, with one of these. So the assumption is, under which we can do this, assume that like this, that this L is being centralized by L centralizes H, centralizes H. Again, what this means is each element of L acts trivially on H by conjugation. So if this happens, then we do have that this semidirect product is isomorphic to H semidirect product K, H semidirect product K, because here we can simply, it's a map from K cross L to L, we can simply restrict that to K with this homomorphism, this K together with L. So the proof for this is also quite obvious, that you can immediately consider the map H comma K comma L, H comma K comma L. Now it is being mapped to H comma K and then comma L. Okay. So that's exactly under this assumption that if in this semidirect product So if we conjugate the each and every element of H by an element of L, then that is not going to change the given element of H. Under this assumption, we can simplify the semidirect product. So thus this two theorem shows that how to simplify semidirect products. In the first case, if the normal factor is the direct product of two characteristic subgroups, and then we have the counterpart for the non-normal factor of the semidirect product. So these are the two simplification theorems which these are the two theorems which are going to be very useful in our subsequent discussions. Okay. So with all these prerequisites, I think now we are in a position to resume our discussion on classifications. So in this course we are going to classify groups of smaller orders, of course, and the question is how small. So in this course we are going to classify all groups of order up to 30. Of course, we do have two exceptions, 16 and 24, because so many possible structures are available there, which makes it beyond the scope of our course. So except 16 and 24, we will classify all groups, both abelian and non-abelian, of order up to 30. And of course, already we have developed some results, let's say, of groups of order PQ, P times Q. So I mean, like therefore not only okay, let me put it in this way, that it's not the case that we can only classify of groups up to order 30 or based on what we have developed so far. Of course, we can go further beyond that. In fact, this general results on PQ, P times Q, this we have already discussed. And of course, as I said, that beyond 30 also we can do for many orders. But however, at least we have to, in a course we have to stop somewhere. So 30 is the finishing line for us. Again, let me remind you that certainly, these are not certainly 30 is not so rigid number that beyond that we cannot actually do anything, based on the tools that I have developed. Okay, I hope I made my point clear. Anyway, so let's start classifications. So let's start with the group of 30 as first. Groups of order 30. Groups of order 30. So let G be a group of order 30. So before I get into the classification, let me again remind you that what are our strategies to classify groups of smaller orders. The first step would be to find appropriate subgroups H and K such that G becomes the semidirect product of H and K. Okay, so that shows us that our given group has to be some semidirect product of some of its subgroups. Then next step will be we will try to classify all possible isomorphism types of H and K. Next, we will try to find all possible homomorphisms from K to H. So thus, corresponding to any isomorphism class of H and isomorphism class of K and then homomorphism phi, we have corresponding to any such H, K up to isomorphism H, K and phi, that this triplet leads us to a semidirect product. So as I said, that corresponding to every such triplet I have a semidirect product, and then what we will do is among this we have to show that which pairs are isomorphic and which pairs are not. Thus we will classify the groups completely, classify all the group structures corresponding to that order completely. Okay. And let me again try to say a few more words. So the first step, as I said, that we have to find appropriate subgroups H and K. So how to find such subgroups? In all what we are doing, because you see that we are working with groups of having order reasonably small. So, for such groups this H and K, usually Silos theorem, I mean H and K will be found using Silos theorems, that is and in our cases these groups are going to be, mostly these groups are going to be some Silo subgroups of the given group G, and since they have order smaller than that of G, so from all we have discussed previously, from that without much difficulty we will be able to classify this H and K completely up to isomorphism. So, that is the classification of H and K, they are done, and in fact most of the cases you will see this H and K are going to be either cyclic groups, in fact of prime order, or having order square of a prime, because in those cases, as I said, that I mean you can recall that we have complete classifications. So, thus we can, I mean in this what we are going to see now, they are the classification of H and K, that is not going to be a big deal, and then we will try to see how many homomorphisms we can. So, for each isomorphism class of HK, then we will try to see how many homomorphisms, of course non-trivial ones are of main interest to us, because trivial one will always lead to the direct product. So, how many homomorphisms we can find, and again that is not going to be a big deal, because that is not going to increase our difficulty, because the groups are already, I mean the groups are already having reasonably small order, and then the final work is we have to classify the corresponding semidirect products, that will be done using the, I mean the isomorphism theorem for semidirect products that we have used earlier. Okay. So, that is how we will, this is a general, I would say the general strategy that we are going to adopt for the semidirect product. It will be more clear once I apply them in several concrete situations. So, this is the first one, let us do that. So, as I said that this H and K will be found using Silos theorem. So, this is 3 into 5 into 2, and for earlier we have seen that if G is a group of order 30, then let like H and K are the Silo subgroups, Silo 5 and Silo 3 subgroups of G. So, this is isomorphic to Z modulo 5Z, this is isomorphic to Z modulo 3Z. So, these are my Silo subgroups, and earlier we have seen that this is going to be normal in G, because this is order 15, and then next so this is going to be a normal one. Then for this semidirect product we have to find an appropriate another subgroup. So, let us take R to be the Silo 2 subgroup of G, that we can of course do. So, let this be generated by this element R. Okay. So, the first strategy, the step that finding H and K appropriately, that is already done. So, therefore, this is the normal subgroup and this is another normal subgroup. Of course, their intersection is, so the intersection is trivial because the orders are relatively prime, and orders are relatively prime. Therefore, and it is also quite obvious that H, K and R, this is a normal subgroup. Remember, that is going to be whole of G. So, that it shows that G must be isomorphic to HK, some semidirect product of HK and R. And remember that inside HK, and HK is a group of order 15 and it is cyclic. So, both subgroups inside HK, both the subgroups H and K are characteristic because it is a cyclic group. So, our situation is precisely of this form. Okay. So, this is like this. Now, you are going to simplify that using this. For that, I mean we are going to use this. So, for that first you have to observe that what are the possibilities for homomorphisms, possibilities for an homomorphism from this to this. Okay. So, since as I said that these are characteristic subgroups, this is going to be direct product of aught H times aught K. Well, so this is here Z modulo 2Z, and here we are going to have Z aught H will be Z modulo 4Z, and then of course here it will be Z modulo 2Z. Okay. So therefore so these are the all possible, like, yeah. So for the isomorphism type, so there is, like, for these two subgroups it has a unique isomorphism, after isomorphism this is a unique group structure, and here it is also a unique group structure. So now we have to just take care of that, how many homomorphisms we can talk about from this cyclic group to this product. And since it's enough to specify the where the generator of this R goes under this phi, and how do we do that? Let me do it here as well. How do we do that? So if phi is trivial, then this is nothing but, so let me do it, phi trivial implies that G is isomorphic to certainly Z modulo 15Z, Z modulo 2Z, so basically isomorphic to Z modulo 30Z. That is not a problem. So let us talk about the non-trivial one. So the non-trivial one, so it will send for R, if phi is non-trivial, it will send R to an element of order 2 here. So since we know the isomorphism type of this automorphism group, so we see that here we can have only 3 elements of order 2. So that is, we can have, there are only 3 automorphisms of order 2 of the group H, direct product K. So in fact we can see this group very concretely. What are these automorphisms? So the first possibility is, like, in order to talk about an automorphism from H and K, well, so maybe we can here we can assume that H, here this H is generated by some A, and this is generated by some B. So in order to talk about an automorphism of H cross K, it's enough to specify where A and B are going. So the first possibility let's consider is A goes to A and B goes to B inverse. Okay. So that is the identity automorphism of H and the inversion automorphism of K. So this is one possibility. The second one is simply it swaps, and the third one is, so we have these 3 automorphisms of H cross K, and already the structure tells me that ensures that these are all the automorphisms. So thus, like for any given, for the generator R of so for the generator R, small r of capital R, either phi are going to be this or that. We have a complete, as I said, we have completely found all the automorphisms. So now in this case, what do we see? So in this case we have that phi r, so if this is phi r, then phi r acts on A trivially, that is phi r is centralizing, so r is centralizing H. So in this case the group structure that we obtain is, so here A, B, well let me rather write it here. So this is nothing but A, B, semi-direct product R, right? So since in the first case R is centralizing H, so this is simply becomes, and here this R, okay. So what is this? So this is Z modulo 5Z, right? and then we have this semi-direct product, and here this is not trivial. This is not trivial because on B this is just the inversion. So this is a semi-direct product of z modulo 3z and z modulo 2z by a non-trivial homomorphism. Okay. So I mean that's exactly the dihedral group. Thus this is basically z modulo 5z dihedral group D6. Okay. What about the next case? In the next case, sorry, here it, okay. Here basically the situation is somewhat opposite. So since H direct product K and K direct product H, these are the same thing. So in this case, like earlier, what we should get is semi-direct product this, and this is z modulo 3z, and this is z modulo 5z together with a semi-direct product is z modulo 2z by a non-trivial homomorphism. In fact, here the inversion one. So earlier we have discussed that this is going to be the dihedral group. So this is going to be D10. Okay, and then let's talk about the third possibility. Let's talk about the third possibility. So this in the third possibility, you see that phi r is inverting every element of this group, which is a cyclic group, right? So therefore, in that case, this is going to be, what we are going to have is something isomorphic to z modulo 15z by a non-trivial homomorphism z modulo 2z, and this is uniquely D30. Okay. And the final thing, we have to ensure that whether all these three are up to isomorphism different or not. So one thing is clear that these are all non-abelian groups. So certainly like they are going to be different from, isomorphically different from z modulo 3z. Okay, and now in order to see that these are, I mean no two of these three are isomorphic to each other, we will look at its center. So here we can immediately see that in the first case the center has order 5. In fact, I mean precisely this is going to be the center. I leave the manipulations to you to verify. Here this is going to be in the center, because at least it will be lying in the center, that is quite clear, right? It is going to lie in the center, that part is clear, because R is acting trivially upon B, and then of course A is also acting trivially upon B, and then you have to just make sure that no other elements than from this are lying in the center. And from Z30, D30 the center follows from the fact that what is going to be the center of the general dihedral group. So if n is odd, then the center is trivial, n is odd. So this is, you can directly see, and if n is even, so this is z modulo 2z up to isomorphism, of course, if n is even. Okay. So the reason for this is, if R is the generator of the rotation group, R to the power n is going to be identity, so R to the power n by 2 is going to be lie in the center. So that you can check. So thus we have seen that up to isomorphism we have exactly 4 groups of order 30, out of them 1 is abelian, the rest 3 are non-abelian. Okay. And here we can of course see that how this theorem, how this observation has been quite helpful to us to simplify the semi-direct products. Okay. All right. So now let's go for groups of order 12, which is relatively difficult. So with groups of order 12, maybe we can finish. So like if G is a group of order 12, let like earlier the H and K that we are looking for will be the silo subgroups. So let H be the silo subgroup, silo 3 subgroup of silo 2 subgroup, and K be the silo 3 subgroup. Okay. So now we know that one of them has to be normal, that we have already proved. So that essentially motivates us to deal two cases separately. So the case 1 is H is normal in G. I will be going rather fast. So in this case, G will be isomorphic to H semidirect product K for some homomorphism. Now for H we have two structures. Subcase 1, subcase 1 is either H is isomorphic to Z modulo 4Z. Okay. So in this case, so H, since if H is normal, then if H is Z modulo 4Z, then its automorphism group is isomorphic to Z modulo 3Z. So therefore, you have only, so subcase, yes. So here we obtain that G is isomorphic to Z modulo 12Z. Okay. Now the subcase 2 is going to be somewhat more difficult. So again, try to understand if H is isomorphic to Z modulo 4Z, then its automorphism group is going to have order 2. Since K is having order 3, so there cannot be non-trivial homomorphism. So only trivial group structure will appear here. Only the direct product will appear here, and that's exactly Z modulo 12Z. Now this is the rather important part. Okay. So what is the automorphism group of H? Now odd H. So as we have already done, this is isomorphic to Z modulo ZL2 of Z modulo 2Z. So this is a non-abelian group, and it has having order 6, so it has to be isomorphic to S3. Now the thing is that inside S3, so like K is having order 3, try to understand. So if phi is a non-abelian non-trivial homomorphism from K to order 3, K to odd H, since odd H being isomorphic to S3, it has exactly one subgroup of order 3, right? If phi is non-trivial, so it has exactly one subgroup of order 3. If phi is non-trivial, then image of K has to be that subgroup. So it shows that there will be exactly one non-abelian group structure in this situation, right? Exactly one non-abelian group structure. And if we remember that already we know a group structure, already we know such a group, namely A4. So if G is in A4, the silo 2 subgroup is having this, the silo 2 subgroup, namely the Kleinfeld group, is of this type. Okay. So therefore, as I said, it shows that there is a unique non-abelian group structure in this situation, and already we know that A4 is a group of this type. So therefore, in this situation, we can immediately see that G has to be isomorphic to A4. I repeat, on a completely different note, we can show that there is a unique non-abelian group in this situation, a unique non-abelian group of order 12, whose silo 2 subgroup being normal, and silo 2 subgroup is normal and of this structure. Okay, the unique non-abelian group, and we know that A4 is such a group, so therefore A4 is all. So this case, when H is normal, that case is already discussed. Now we shall go for the other subcase, and maybe with that I will finish. Maybe with that I will finish. So the case 2. Okay. And here we see that these two are not going to be isomorphic. Okay. So let's come to case 2. in case 2 k is normal, k is normal, okay. If that is the situation, what we, so therefore odd k is isomorphic to z modulo 2z. Once that is there, so next task is to find number of homomorphisms from H to odd k. Okay. So now we do have 2 possibilities for H as well. In the subcase 1, H is isomorphic to z modulo 4z. H is isomorphic to z modulo 4z, and so in this case how many homomorphisms we do have? So in this case we see, of course the trivial one leads us to k is of the so it is isomorphic to k semidirect product H, right. So z modulo 3z, z modulo 3z, when it is trivial, z modulo 4z, and if phi is non-trivial, then we have, so since this is having order 2, so there is a unique non-trivial homomorphism from H to odd k, right. This we have already seen, and with respect to that automorphism, the group that we make is z modulo 3z alpha z modulo 4z. So alpha is the unique homomorphism from z modulo 4z to that the unique non-trivial automorphism of k. So this semidirect product we have already seen, and certainly this is this is a non-abelian group because alpha is non-trivial. So again this is isomorphic to z modulo 12z, and we have already argued that this semidirect product is not isomorphic to A4. So thus in this situation we get another isomorphically different group structure. Now let us come to the second subcase. So here the situation is that when H is subcase 2, when H is H is isomorphic to z modulo 2z, you see, like as I said, that the finding H and K will be by the Sylow's theorem, and the structure of H and K can be found from what we have done earlier because they have reasonably smaller order, and the number of isomorphisms is also not quite difficult to find out. It's not difficult to find out all the isomorphisms, at least how at least if not all, if not explicitly I can determine all the isomorphism, then we'll try to see the images of H, because if they are the same or they are conjugate, then we'll get a unique structure. Okay, so let's continue this. Okay, so therefore now so this shows that there exist 2 elements H in H such that H is the Dirac sum of this, right. In fact, not if we take any 2 distinct elements of order 2, then it will be there. So we have the liberty to choose A and B appropriately. In fact, that's what I am going to do. So here if we consider an homomorphism from H to odd k, if phi is trivial, then we don't have anything to do. So in that case we have this structure. In fact, this gives the phi is trivial, implies, so z 3, Z3 direct sum, Z2, Z2. Okay. So, in fact, that the two case, in fact, the abelian ones are also coming out of our analysis, the abelian structures as well, but but those are the trivial ones. And if phi is non-trivial, then so this is isomorphic to Z modulo 2Z. Okay. So, if phi is non-trivial, then what is going to be the order of the kernel phi? The order of the kernel phi has to be 2. I repeat, whatever be the phi, whatever the phi, so whatever phi we consider, kernel phi is going to have order 2. Kernel phi is order 2. Okay. So, let this be generated by A, and then we can choose B lying inside H, and we can choose B from the complement of A, and if we choose B, A and B like this, then we must have this. Okay. So, B can no longer be in the kernel. So, now everything depends upon that where we are sending B to, and let me do it here. So, A is in the kernel, B is not in the kernel. So, then what are we getting here? Our situation is that the possible group structure is of this form. So, H is the direct sum of A and B, and A is in the kernel, that is A acts on B trivially. So, hence we must have that, hence we must have that K cross B, just A is acting trivially, right? Yeah. So, the action of A is trivial on B. So, therefore, that part is centralizing K, hence we can simply take it out. So, this is what we are going to have if I am not wrong. Okay. And what is that? A is isomorphic to so A is isomorphic to Z modulo 2Z, A is isomorphic to Z modulo 2Z, of course. So, this is Z modulo 2Z, K is Z modulo 3Z and semi-direct product, B is also Z modulo 2Z, yes. Okay. This is what we are going to have, and this is certainly D6, right? D6. Okay. So, it is certainly D6. Well, I think here we can slightly we can slightly change things. So, this we can bring this side as well. I think that will be perhaps better. Yes. Then we have a much more concrete description, because we would like to view this as D12. So, maybe this one is a better idea, and B is centralizing A. So, therefore, there is no problem if we consider this, right. There is no problem in that. So, this is how do we see that? We should bring, okay. So, this is K is isomorphic to Z modulo 3Z, right? Yes. So, this is isomorphic to Z modulo 6Z, and now we have Z modulo 2Z here. This isomorphism is homomorphism is non-trivial, hence thus we obtain that this is D12. Yes, now we are done. Okay, so in this case, in the second sub case, when H is this, we see that whatever phi we take, whatever non-trivial homomorphism phi we take, the semidirect product that we are going to get is always D12. So one thing is clear, that since the image will be always 2, you will have exactly one non-abelian structure, that is quite clear. But even if we do not use that, just by directly simplifying the semidirect products using the two theorems we have seen, we can immediately see that this is we always get D12. Okay. Okay. So therefore, we see that we have only these structures up to groups of order 12. So what are the structures? We have two cyclic structure, namely Z modulo 12Z and this, and then we have two abelian structures, Z modulo 12Z and this, and exactly we have three non-abelian structures. One is this, another one is D12, and the third one is A4. Okay. So in the remaining a few minutes in this lecture, I will be talking about groups of order 8, because like when P is an odd prime, all groups of order P cube has been completely classified. So, but the even case is to be, as I said, it is to be dealt separately, which we will be doing now. Of course, the abelian ones are already been taken care by a structure theorem. So we can now just focus on the case when G is non-abelian. Okay. So since G is non-abelian, G must have an element of order 4, because if like a typical element in G can have order 2, 4 or 8, since we have assumed non-abelian, it cannot be 8, also it cannot be 2, because it is a well known exercise that if every non-empty element is having order 2, then the group has to be abelian. So that means there has to be an element of order 4. So there must be an element of order 4. Yes, so now the point is that well, it's customary to, maybe we should rewrite it by 4. So now we have two cases. One is whether there exists a J outside this subgroup with order 2, whether it is there or not. So if this is there, then we see that, like, of course, that the intersection is going to be trivial if this is there, and I mean, of course, like every element can be written as a product of something from here and something from this subgroup. So I mean, this here I am getting somewhat sketchy and leave the justification for the conclusion to you, that if this is the case, then these two subgroups satisfy all the criteria for being of the recognition theorem. So in this case, we obtain that G is isomorphic to semidirect product of I and J, and that immediately tells us we have already two possibilities. Either we have, well, since it is non-abelian, we have to begin with we have assumed, so certainly this cannot happen. So this is having Z modulo 4Z, Z modulo 3Z, it's non-abelian, so it's non-abelian, Z modulo 4Z, Z modulo 3Z, this has to be non-trivial, so we must have D8. Okay. So in the first case, the group structure that we obtain is D8. The next case, that every J outside this group is having order 4. So every J having order 4. So this case, so what do we get in this situation? So So, in this situation the following are immediate. So, the intersection cannot be trivial, because then the product of these two groups will be having order 16. So, the intersection must be having 2. In fact, from this it follows I square equal to j square, and also this is having order 4, this is outside j. So, if we pick any j here, then g must be this 1 I square I cube, and then of course multiplications by g, j I j I j I cube j. So, this has to be there because g is outside this group. So, in this situation we can immediately see that, so like j and I cannot commute, because if j and I commutes, then any power of j will commute to any power of I. So, that will make g to be abelian. So, therefore, j in this case what you can see is j I is nothing but I cube j. So, now you have to I have to tell you what this structure is. So, this is left as an exercise. So, the hint is that if you treat this as symbolically as -1, and if you denote this by some k, then like as I said, that symbolically treat this as -1 and denote k for ij, then you will see this is the group structure here is exactly isomorphic to Q8. So, the formal thing is for the formalities I am leaving to you, that in this case G is isomorphic to Q8. So, what you have to do is, let me again tell you orally. So, in this Q8 we have generators I, j, k, right. So, map I and j to those I and j of Q8, and then it will force that this I j will be k there, because you see that like symbolically if you just write this as k, then you try to rewrite all the other things, then you will see that the group table or whatever the compositions, they look like exactly similar to that of Q8. So, formally map the I and j of here to the I and j of the Q8, then once you do that, and of course map the other elements accordingly, because you have to consider homomorphism. So, then you will see that that map, that homomorphism that you consider in that manner becomes an isomorphism between G and Q8. Okay. So, the motivation for that is simply like treat symbolically, write this as -1 and write this as k, and then you with these two notations you write down the all possible combinations, compositions of two elements of this group. You will see it will entirely look like that of Q8. Okay. So, to put in formal terms, you consider the homomorphism mapping I and j to that those I and j of Q8, and of course other elements accordingly, then that homomorphism is going to be an isomorphism. Okay. So, therefore, up to for order 8, what are the only group structures? Z modulo is Z after isomorphism. We have Z modulo 4Z, Dirac sum Z modulo 2Z, then we have Z2, Z2, Z2. Okay. So, these are the all abelian ones, and as non-abelian ones we get only D8 and Q8. Okay. So, the only case that we are left with earlier, namely when while classifying groups of order p cube, the only case that we are left with was when p is even. So, that case is now done here. Okay. So, I think with that I will finish this lecture.